looks like Ahmed is popular. I didn't know that. Today's speaker joined us after earning his bachelor and master's from Forsyth University in politics and famous sport, Forsyth. Ahmed has done a great job. I don't know if he went from his presentation, but he has done a lot of experimental work as well as extensive numerical modeling. I hope he learned a lot through his studies here, and he'll be able to take this technology with him when he goes back to Egypt. So without taking too much of his time, I would like to invite him to present his great work on behavioral wind turbines for the mega size.
Good morning, everybody. Thank you for attending the lecture at the early morning. So my public lecture will be on the tidal investigation of hybrid foundation system for offshore wind turbine. It will be under supervision of Professor Shamil McCarthy. Today outline will speak about different points. First one will be introduction. We'll speak about the problem, about the green energy, about the different type of offshore foundation systems, why we are using this. Then the purpose of our study, the hybrid foundation system, what we are going to provide through this work. Then we're going to do wind tunnel test, and we are going to see while you are doing the wind tunnel test, how we are going to use the load from wind tunnel test to be applied in numerical parametric study that have been done by 3D dimensional model by using ADACAS program with different cases as parametric study. Then we will see what's the meaning of 1G scale down test, why we use it, why we are going to use our analysis from wind tunnel test and from numerical analysis to be applied in 1G test. Finally, we'll have the conclusions. We know all that there is increased demand in energy all over the world, and green energy can be considered one of the good choices. Wind energy can provide us with green energy. Offshore wind farm can be considered as preferable solution due to high wind intensity offshore and less community problems. But the problem that 35% of the total cost just going for the foundation. So if we are able to reduce this cost, we'll be able to reduce the total energy cost. We can see here different offshore foundation types, starting from gravity-based monopile suction casing. This is depending on our experience from offshore foundation, which came mainly from oil sector, which will be different than the wind energy sector. We can see here this figure from NREL, National Renewable Energy Laboratory, where it shows the relation between water depth in meters and substructural cost. We can see here with increasing the water depth, substructural cost will be increased. We can see here with shallow water depths, the most profitable foundation system will be monopile all gravity foundation. With increasing the water depth, we can use 3-bolt foundation and jack trusses. Then we can go for floating structure, and both of them will be out of our scope. We'll just focus to shallow foundation system, less than 20 meter water depth. So our two major foundation systems will be monopile and gravity-based. For gravity-based foundation, we have different type of gravity-based foundation systems can be laid to our shapes. The main thing here to be constructed onshore, then will be transferred offshore to be erected to reduce the cost of installation. We can see here, it depends in its own way to adjust the open technique. It can be added here by some surrounding soil to increase its self-weight. It has been used in Baltic and North Sea where they have experience in this type of foundation from the oil industry. We can see also the monopile foundation system, which will be steel pipe with diameter between 4 and 6 meters, with length between 20 and 40 meters. And this one has been used in Horns Rev wind farm in Denmark, and this is one of the largest wind farms in that. And we have also in London Array wind farm. When we started our study in 2011, one of the largest wind turbines was 2.3 megawatt wind turbine. It has been used in Horns Rev 2 wind farm. And this wind turbine, you can see that the hub height is 68 meters, the rotor diameter is 93 meters, and the most important thing from our point of view is diameter at the base, which will be 4 meter diameter. So we need to have foundation with diameter 4 meter diameter. But as we can see here from this figure, that was it's represented by NREL. That was increased on the rotor side, the cost per megawatt will be reduced. So the cost here will be structural cost, installation cost, operation cost. So the main idea now is increasing the size of the wind turbine. So now we can see the 5 megawatt NREL wind turbine, and NREL is National Renewable Energy Laboratory. In this wind turbine, we used hub height of 90 meters. The rotor diameter is 126 meters, and the most important thing, we increased the tower base diameter as 6 meters. So we need to have foundation from 4 meter diameter to 6 meter diameter. We can see here different foundation system. We can see the monopile with diameter 4 meters that already have been used and to support 2.3 megawatt wind turbine in Horns Rev wind farm in Denmark. We can see the monopile diameter equal to 6 meters that has been used, suggested to be used by NREL to support their 5 megawatt wind turbine. And we can see our hybrid foundation system. Our hybrid foundation system will be a combination between steel monopile with diameter 4 meter, which will be connected with upper part, which will be 6 meter diameter, to be able to connect with the tower of the wind turbine. We connect both of them by concrete plate to be able to increase its lateral and rocking stiffness. We can see that the plate sometimes will be with revs, sometimes without revs, to see the effect in stiffness. So we have seen the 4 meter diameter bar already used in the Horns Rev. You can see the 6 meters that's suggested to be used, and our 2 hybrid foundation system, which will be smaller monopile. This is isometric view for the hybrid foundation system. We can see this is hollow steel pile, 4 meter diameter, as we said. The upper part, which will be support to resist up to 20 meter water depth. We can see the upper part will be 6 meters to be able to connect with the tower. We can see here the concrete plate, which will be connected all parts together. We can see here different shape of the hybrid foundation system. How we are going to install this hybrid foundation system. So we divided this hybrid foundation system for several parts. The first part will be driven pile with 4 meter diameter. After installed, we add this part, which will be constructed onshore, which will be the upper part, 6 meter diameter with 20 meter length to be able to support 20 meter water depths, connected with this concrete plate. We connected both of them together, so this is part 1, this is part 2. After adding 2 parts together, we can add cast in place concrete as part 3. So this is the 3 steps of constructing the hybrid foundation system. So what is the purpose of our study? We need to represent actual base load at the base of the wind turbine to be able to use it as design of foundation system. We want to provide hybrid foundation system. This hybrid foundation system able to carry the larger wind turbine that's already provided now. This hybrid foundation system will be combination between steel monopile with the 4 meter with concrete plate to be able to increase its stiffness. There will be a reduction in the material. It can be as a saving in this hybrid foundation system. This hybrid foundation system also will be able to increase the capacity of existing foundation systems. We already provided guidelines and recommendation for this hybrid foundation system. So through our work, we will start to get the load at the wind turbine. We will get this from wind tunnel loads. Then the wave loads we didn't calculate it, we get from NREL report for the same case, for the same water depth. Then our hybrid system will study it as parametric study abacus program for different cases. Then the 1G test in the structural lab. So the wind tunnel test. We have done the wind tunnel analysis and boundary layer wind tunnel test here at Western. Generally, to get accurate load, we have several methods. We have experimental, we have theoretical, we have field. So experimental should be the wind tunnel. We have theoretical by using some program as CFD, and field and false scale test. In some cases, would be so expensive. So for our experimental, we just choose the wind tunnel test. Unfortunately, there is a minimal information about the actual loads at the foundation coming from the wind turbine, and they usually use as typical loads. So that's why we already making the wind tunnel test to be able to get accurate load at the base of the wind turbine to be able to apply it on our finite element analysis. We adopted the 5 megawatt NREL wind turbine to be as our reference wind turbine to calculate the loads here. And this is not actual wind turbine, but this is a wind turbine for research purpose represented by NREL. We can see here, this is the shape of wind turbine. Yeah, small scale here. So it's 5 megawatt wind turbine, it's 3 blades. The rotor diameter is 126 meter. The hub diameter is 3 meter. The hub height is 90 meter. The cut in, cut out speed is 3 meter per second, 25 meter per second, and the rated wind speed is 11.4 meter per second, and the pre-cone angle is 2.5 degree, and the different weight of each element is already provided. So we have done small scale down model, 1 to 150 in machine shop here. As you can see, this is our scale down model from aluminum. Tube with Rothschild cladding. We can see we can move different configuration for the plates and also different angle of attack. In order to get it for force balancing, it needs to be so light and so stiff at the same time. We tested at wind speed and the wind tunnel is 3.6 meter per second. We have different configuration. We have configuration A, as we can see here, which will be 0, 120, 240. And we have configuration B, which will be like this, as 60, 180, and 300, with different plate angle, which will be between 90 and 50. Before we start, we have done our calibration for our model by applying known loads to be able to see the load here at scale. And we can see here, this is the angle of the plates. This is the load that we already have been used for scale down in the wind tunnel test. This is the force in fall scale, related to force in the lab, related to the actual wind speed and the wind speed in the lab. And 150 will be our geometrical scaling, and the moment fall scale, moment in the lab, also related to the wind in the field and the wind in the lab. 150 will be our geometrical scaling, and also relation here to represent the time in the wind tunnel and the time in the actual test. After we have finished our wind tunnel test with different angle of attack, we already will be able to get time history as 6 components at the base of wind turbine. We can see here, this is Fx, and this is the time between 0 and 5,000 seconds. This is scaled up between 2,000 seconds, 2,500 seconds. So we'll be able to get actual time history for the 6 components at the base of wind turbine. We tested wind turbine at the parted position. At the actual wind will be relative to 47 meters per second. We can see here with different angle of attack between 0 and 180, we'll be able to get base reaction as Fx, Fy, Fz, Mx, My, Mz. This is the mean value root mean square and the peak value, and we can see that of course the maximum Fx will be at 0 and the maximum Fy will be at 90. We compared our result with FASTER program, which will be the program used by NREL in their analysis. We can see here our results will be with blue and the results will be in orange. We can see good agreement between our result and the result FAST for the mean value. And this is our peak value, which will be between 2.5 and 3.5 peak factor of the mean values. Numerical parametric study. After we already got our base reaction from the wind tunnel test and we scaled it up and we already got our wave load, we'll be able to apply it on our numerical analysis to get accurate calculation for our design. We need to present several foundation systems. The first one will be monopile, which will be a reference pile for us. with diameter 4 meters, which will be already have been used by Horner's Rev wind farm. But in order to be able to scale and to compare each system with each other, we already added this part, which will be 6 meter diameter, to be able to support the other part, and it's the same, to be able to the same inertia. So this part will be 6 meter, this part will be monobile 4 meter diameter. This is the mud level, this is the sea level, so we can see that the water depth will be 20 meters, and this will be different lengths. This is the monobile with diameter 6 meters that's suggested to be able to resist 5 megawatt wind turbine suggested by NREL, and we can see the monobile diameter 6 meter to resist 20 meter of water depths and with different pile lengths. And then our hybrid foundation system, which will be smaller pile as a monosteel pile with diameter 6 meter, and the upper part with diameter the monopile with diameter 4 meter, and the upper part with diameter 6 meter, with water depths 20 meter, with different lengths. And you can see here we changed also the blade diameter from 12 to 16 meter. And as we said, the blade sometimes will be without ribs, and sometimes with ribs to see the effect of adding or removing the ribs. So our different foundation system, the monosteel pile 4 meter diameter, monosteel pile 6 meter diameter, our hybrid foundation system. We have done our barometric study by changing the lengths between 16, 24, 36 meter. We changed the blade diameter from 12 to 16 meters. We already have done several load components as 6 components, as 6 forces, 3 forces, 3 moment coming from the wind tunnel test. Then we have done our analysis as 3 components, just vertical, horizontal moment, and then 2 components, as most of studies as in the foundation design just use 2 components from the wind tunnel test, from the wind loads. We have done also displacement control horizontally and vertically to be able to get the actual capacity of the system. This has been done for different foundation systems.